Okay, juniors, did you get your coins? There you go. All right, everybody come on and get settled in. Excellent, excellent.
Yeah.
I'll see you after. The one is taking that chair. They're really good.
No, not that chair.
I know. Who is taking that chair? It's this. Wait a minute.
Waiting for.
Oh, I
Able subway chair. You don't have
Yeah. Thanks for patience.
Okay, are we filing it? You guys did really well. That's a lot to do in lab, but it's teaching you how to do the stuff you're going to be doing a lot of this year. Good work, very good work. And look, we used fire and we were safe. Excellent. Yep, this was good. Okay, let's make sure everybody gets a spot and is situated and is ready to go. Are we good? Do you want to stand or are you looking for a spot? Okay, wherever you're comfortable. If you want to sit. I also don't want anybody to be like, I can't find a spot. There you go. There's a spot right there. There's a spot right there. A spot right there. Maybe a spot back there. One right there. We got lots of room. Okie doke. So let's roll with this. So we are doing what is chemistry, describing and classifying matter. Be sure if there was anybody absent from your lab group today, I think the only absences were Colin F. and Ethan. Yeah. I knew Colin F. would be gone. I don't know what's up with Ethan, but I'll find out. So anyway, you can always get their data, huh?
He said that he feeling very.
Okay, there you go. Yep, it's going around. It's definitely going around. So I'm not surprised, you know. Yep. Keep yourselves healthy. Let's make sure that nobody is trying to. Now, let me tell you this. In case Colin or Ethan attempt to join live during class, I'm so bad about noticing that someone is ding-donged and says they're here in Zoom. So like, feel free to go, yo, somebody's there, because I get wrapped up and I don't notice they're there. Yes, sir. Not today, I don't think. You live for the Menti, don't you? You can just place them down there on the floor between the couch and the table if you'd like. There you go. Okay, so let's roll. Describing and classifying matter. So first things first, before we begin, I want to give everybody a reminder because it became an issue for the first time, obviously, at least. So about the Unit 1 test and for all other work in this class, for everything that you do. So here's a point. I do have a life outside of this class. I actually do things aside from, 10 a.m. to 1:30 p.m. on Tuesdays. I have a life and a family and places to be. And you've got a future. And the reason I'm reminding you of that is because I would prefer if you not suck my life away by submitting answers you used AI to generate for you. And here's why. So if I'm grading for me, selfishly, if I'm grading your test, I can answer your questions, usually grade your answers, in like 1 to 2 minutes, usually. Sometimes I take some time to add comments. A lot of you are going to see comments on your test. I'll add comments whenever I think it'll be helpful to you. That takes a little more time, but usually it's 1 to 2 minutes. But if I read an answer and it appears to be generated by AI, then I got to go check it. And our policy says I'll run it through 3 generators. This last week, I used between 4 and 5 every time an answer came up that looked questionable to me. So now those 1 to 2 minutes are 10 minutes a piece, and there's 24 of you. And there's usually like 20 some odd questions on a test. So you see how much of my life will be gone? Gone. I'm already getting old, y'all. Let's not make it worse. And then the other thing is, don't sell yourself short. Do the work. I suspect this was an issue of will she catch it game. Got it. Do the work and practice a good work ethic. So it's going to serve you well in the future. And that's true about everything. Work ethic applies to every work you do. I don't care if it's sweeping your kitchen at your house or whatever. Do a good job, do a thorough job. Don't cheat, don't cut corners. Do good, thorough, well thought out work. It's worth it. The other thing is it's very tempting to take, because you're doing your test online. So it's very tempting to cut and paste the question and just get your answer off the internet, because you can just open a tab and do it, right? Real tempting. Problem is when we do our midterms and our finals, that's not an option because you're in here in person with pencil and paper. And if you haven't learned anything because you've been cutting and pasting all semester, you're going to have a problem, right? So let's not have that problem. All right, so just keep that in mind. Please, please, please. I'm not one of those teachers that's going to tell you to never touch AI because that's really dumb. That's like telling students to never touch their cell phones, which is really dumb. These are tools that you should learn to use appropriately, right? Cool. Excellent. We're all in agreement. All righty. Now, I have about 6 tests left to grade, but so far your class average is a 92.9, which is very good. I think the juniors was a 92.6 or 7. So real close. This is a good first test grade. A low A is good. I don't want everybody getting 100 and I don't want everybody failing. That's bad. You want a little bell curve, and this one should be a slightly higher average than all of the future tests because this test is easier and has less content than all of the future tests. I like my averages to be 85, somewhere around there, you know? I'm not, if I get 1 or 2 that bomb a test, that's fine. Get a couple that ace it, that's fine. But you like a bell curve, right? And you see your little averages roll through. All right, so we're going to start with a question. We touched on this briefly last week, but now I'm going to actually show it to you straight up. So here's your question. Do you think there are good chemicals and bad chemicals? And if so, how do they differ? So this is opinion. You can't get it wrong. PJ, what do you think?
I would think that if there were bad chemicals, there would be like the radioactive ones that kill people.
Okay.
But they can still be like used for things that are helpful.
Yeah, that's good. What do you think, Colin?
Good chemicals are helpful or very harmless.
Okay. Harmless is a good word. Harmless versus
Harmful.
harmful. Okay, that might be a better way. Asher, you have an opinion?
I'd say there are no good chemicals and there are no bad chemicals.
There are no good chemicals or no bad chemicals. We just won't categorize chemicals that way. Lucas?
The good chemicals are the ones found inside foods.
Carrots. I like that.
Here.
Excellent. Yusuf?
Harmful and harmless.
Harmful and harmless. You think that's a better way to categorize them? Okay, so, James. Aha. Very good point. Good and bad are subjective words, and we try not to use subjective language in science. Very, very good. That's a great answer. I just use subjective good, but I'm being subjective. Yeah, what Asher said, harmful versus not harmful, right? All right, so I told you about this article last week. Here it is. This is from 2019, so it's not that old. Study finds almost 40% of people in 8 European nations would like to live in a world where chemical substances don't exist. All right, so I'll read this to you, and I want you to listen carefully to the language that was used and the responses that were given. So the little tagline says, such scientific ignorance is common in the US as well and can have harmful influence on government policy. A recent study published in Nature Chemistry finds that 39% of respondents in 8 European countries say they agree with the statement that I would like to live in a world where chemical substances don't exist. Another 39% say this should say they, I believe, slightly agree or slightly disagree with this statement. Similarly, 40% say I do everything I can to avoid contact with chemical substances in my daily life. As a study authors, Swiss academics Michael Siergist and Angela Berth point out, such chemophobia reflects stunning scientific ignorance because human life would be virtually impossible without chemicals. Indeed, pretty much everything we touch or use is a chemical or combination of chemicals. Even if we limit the definition of chemicals to artificially produced substances as opposed to naturally occurring ones, most of the products of modern industry and agriculture routinely used, such as materials, they are on average no more dangerous than natural substances. If you truly do everything you can to avoid contact with chemical substances, even just artificial ones, you would probably have to return to the Stone Age lifestyle. Seargis and Birth note that many claim they do everything they can to avoid chemical substances, although they clearly and most likely unknowingly rely extensively on products from food to cell phones that would not be possible to manufacture without synthetic chemicals. If you're reading this post on a smartphone or a laptop, you're using chemical substances right now. So there's a word in here, and this is a great example of why it's important to know your Greek and Latin parts of speech, roots, prefixes, suffixes. And the word is chemophobia. Anybody want to give a shot? What is it, Caden?
The fear of chemicals.
And how do you know that?
Phobia means the fear of.
There you go.
You sounded out, imagine it's chemicals.
Yep, chemophobia. So fear of chemicals. That's a thing. Yep, clearly. So there you go. We talked about this a little bit last week, but there are plenty of people in this world who are just scientifically illiterate or scientifically ignorant. So scientific literacy is hashtag life goals. I would love for you to be the kind of person that looks at one of these people and goes, dude, stop. What are you talking about? What do you mean you want to live in a world without give me your phone, take your clothes off, run through the streets naked, because that's what you're going to be doing. Like everything I mean, if you're wearing anything with polyester, and probably everybody is right here, any of those things, like, right? These are all chemicals. Yeah, you could pull an Archimedes and yeah, there you go, right? Who was Archimedes? Who remembers what Archimedes did? Yeah, Liam, you remember the bathtub guy? What's the story, the legend behind Archimedes?
I don't know, like figure something out, but he was in the bathtub, so he ran through the street and
Yeah, what was he trying to figure out? You remember?
something with ships, but it's all the water.
We did ships at the end. We talked about ships. Do you remember, James? Yeah, density and volume. So basically it was like the story is the king said, here's my crown, and I feel like the goldsmith who made it shorted me, and it's maybe not all gold. So how do you figure it out? So it had to do with putting the crown in the bathtub, watching the water displacement, all that kind of thing. So that's the whole story with Archimedes running through the streets naked. Because Eureka, jumped out of the tub and ran. And last year when we did this concept, ships, you remembered, we had our lab that was raising a sunken ship, and we had like a whole pirate theme for a day. It was Halloween actually, and it was fun, right? Cool. All right, so what's chemistry? Let's get some terms defined here. So blank there, blank and the blank in which they're involved. This is chemistry, is the study of what? Jordan?
Chemicals.
Chemicals. Their what are we going for? Yusuf?
Properties.
Their properties and the what in which they're involved. Hayden?
Reactions.
The reactions in which they're involved. Okay, we're going to be doing lots of reactions this year. Didn't get any reactions today. Oh, don't worry, they're coming. We will make things change color. We will make things get hot, get cold, grow things. It's going to be much fun. Yes.
I make something explode.
We actually will probably make a couple things kind of explode, but that'll be an outdoor event if we do it. Won't be too much, but we probably will do a little, if only if we can make it fit in. I did make, dare I say this? There are common chemicals you can use that can make things explode. Like you don't need a lab permit or an account with Carolina Biological. You can, yeah. So some of that, do you know?
What might outside plus water?
There's one. Yeah, there's one for sure.
What might that be?
Yeah, you're gonna Google that. I'm not participating in your terrorism, Liam. All right. All right. Yep. All right. So what is any substance with a defined composition? PJ?
Solid?
A solid. Well, in this place, we're just looking for the chemical in general. So let me ask you this. Is hydrogen a chemical? Who says it is? Who says it's not? It is. Okay. Now, is water a chemical? Yes? Okay, so, but water is composed of multiple atoms, right? And hydrogen can just be by itself or with a buddy or whatever. So how are they both chemicals? Do you have input? Compounds versus elements, right? But in general, we have the umbrella of chemical and we also have the umbrella of substances. So substances is kind of a more nebulous word than chemical, but pretty much everything is a chemical, if we're going to define it. Okay. So what would this be? A characteristic of a substance that does not involve a chemical change, such as density, color, or hardness. What do we call this kind of a characteristic? Do we know? Anybody want to take a guess at it? Andrew, you want to guess? A physical property. You're there. Yep. All right. A physical property. So a physical property doesn't involve change, chemical change. So it's something like density, color, or hardness. So if I take, where is it? I got all these papers over here and blank paper. Somebody give me a physical characteristic of the paper. Yes, PJ.
It is thin.
It is thin. What else, Asher?
It
It is long. Okay. What else?
Flexible.
It is flexible. All right. We have some things here. Yes. Yes. Lucas. Yes.
is white.
It is white. Okay. Katie.
It's fragile.
It's fragile. All right. Liam, give me one more.
A stripe.
It has stripes. All right. Excellent. Would you describe it maybe as flat? Could you say that maybe?
Yeah.
Kind of. It's not really like it's 3D, but still it's very thin, right?
It kind of can be.
All right. So you could definitely describe it as like thin. All right. Is it flat any longer?
No.
No. Okay. Did I change something about it physically or chemically?
It's-
Physically. If I set it on fire, am I changing something about it physically or chemically?
Chemically.
Chemically. Yeah, both actually. Yeah, but for sure chemically because it's going to burn, and flammability, combustibility, those things are chemical. All right.
Turning into carbon, right?
Yes, turning into carbon. So, and other things, but a lot of carbon mostly. So what do you call a change in matter from one form to another without a change in chemical properties, Asher? Oh, he had it and then he didn't have it. All right, Colin.
State change.
There you go. State change or a phase change or a physical change. Okay. So if I have an ice cube and I leave it on the table for an hour, what's going to happen to it? It's going to melt. Okay. It's going to melt. And is it going to change chemical properties about it?
No.
Is it still water?
Yeah.
Yeah, it's just water in a different state, right? Or a different phase. So it went through a physical change or a phase change. When I crumpled up the paper, that was a physical change, right? It wasn't a chemical change. So then how about a change of a substance from one physical state to another? This is like we said, change of state or phase. So you can use the word change of state, change of phase, kind of interchangeably. Okay. All right. Now, physical states of matter. Our big ones are going to be right here, solid, liquid, gas. They're not the only ones. Okay, there are some that you only see under certain conditions here on Earth, and there are some that you kind of never see on Earth, but they still happen. Yeah,
Plasma.
plasma is the one that you can see every so often. When do you see plasma, Liam?
Space.
In space? When can you see it here?
I don't know.
You know, James?
Those little plasma balls.
A little I have a little plasma ball upstairs, Drew.
Like two rays right next to each other,
Oh yeah,
and you put it inside the microwave,
yep.
it goes like,
Yeah, you can see plasma then. That's true. Lucas.
there's a little bit of plasma and fire.
Yeah, there's a little bit. Xander.
Lightning.
Lightning. There's the big, real obvious one, right? Like when you get lightning zapping around, you see in the plasma. Yeah.
Fluorescent light bulbs.
Fluorescent light bulbs. There's another good one. Yeah, we went over those last year too, right? Okay. So a solid has fixed particles. We also say it has a fixed shape and a fixed volume, right? Hey, Drew, would you let your dog in the gate? He's at the gate. Do what? Oh yeah, thank you. All right. So solid particles have fixed positions. Some of the first chemicals that we're going to be talking about are salts or ionic compounds, and those have a crystal lattice. So when things are in a crystal lattice like that, they tend to be very brittle. okay, but they have fixed positions. And because they have fixed positions, like I can thump on the side of my desk, and unless I thump really hard and I kind of displace some of the matter, nothing's really happening because it's a solid. So it has a fixed shape, fixed volume, and the particles have fixed positions. For a liquid, your particles move around past one another. They move around. And we also say liquids have what about a liquid volume? Is it fixed or not fixed? We say it's fixed usually, but how about its shape? Is it shape fixed? No, it takes the shape of what? It's container, right? So if you have one of those nice, standard square looking like aquariums, you could put 5 gallons of water in there and it's going to be like a little cubular or prism or rectangular prism, whatever shape you have. If you pour it in a pitcher, it's going to take on whatever shape the pitcher has, right? Do what?
Like a cylinder.
Yeah, cylinder. You watched the water in lab, Drew. You watch the water in lab change shape a couple times, right? But the volume, when you move that volume from your flask to your graduated cylinder, like the same volume of water moved, but obviously its shape changed. So liquid forces lead to surface wetting and capillary action. Surface wetting is probably more apparent than you think, but if you touch it, it's wet, right? Here's a question. When a fish is in, how does it go? Is a fish swimming in the water wet?
Yeah. Yes.
Yeah, it's in the.
But when you pull your hand out of the water, your hand is wet. So is it wet when it's in the water?
Yeah.
That's one of those people. That's one of those things you can see these videos of social media arguments. No, it's not wet when it's in the water. It's only wet when you come out and you're wet. Now,
Those dumb arguments.
What's
is
wet?
Water wet.
yeah, what is water wet? Exactly.
Water.
So that's surface wetting. Does anybody know what capillary action is? Do you know? Anybody? Shh, guys in the back?
Is that like spicy foods?
No, so capillary action, you're thinking capsaicin.
Oh.
Goodness, very similar. Okay, so capillary action. Yeah, ever been to the doctor? They don't do it this way quite so much anymore. But when they used to do a finger prick to check a little blood sample for like anemia is usually what they're looking at, it's hemoglobin. They do a little finger prick and they used to take this tiny little glass tube and they touch it to your finger and the blood goes whoop right up the tube. That's capillary action. That's because there's some attraction between the liquid and the little glass tube, and that attraction moves it right up. It's, in this case, you've got water in your blood, and it's really great. The hydrogen bonds in particular, you can see where they stick to things. And also it's got surface tension. Okay, where did you see surface tension today? Katie.
When you pour water.
Uh-huh.
Into the, I can't remember the name of
In
it.
the graduated cylinder? Yep.
You could see surface tension.
Okay. And it was shaped like this, right? You see that meniscus in your graduated cylinder? And that's because you've got surface tension and capillary action working together. So you've got, it wants to go up the sides of the container, right? It wants to go up. Now, if you actually have that slight curve like in a beaker or any other container, but the container is so wide, the surface area is so great that you can't perceive it. But in a graduated cylinder, you can really see it. And when you use a 10 milliliter graduated cylinder, which is really tiny, it's like pinky sized, you can really see that meniscus. Do you measure from the bottom or the top? The bottom, right? You measure from the bottom of the meniscus. There you go. Yep, that's how you do it. So liquids have surface tension and capillary action and surface wetting. And then lastly, gas. Gas particles are essentially independent. They're just bumping around, right? They bump into each other all the time. Do we say that gas has a fixed volume and what do we say about volume for gas? Is it fixed volume?
No.
Not so much. And is it a fixed shape? No, it's going to take the shape of its container. A good example of gas not having a fixed volume. Today you use the propane tanks in lab. That is propane under pressure. If you were to let all that propane out, it would just fill the space, right? It would fill up, it would go all over the house, right? But if you keep it under pressure like that, then you can use it to your advantage, right? But we use this with aerosol cans, oxygen tanks, propane tanks, all that stuff, right? Okay, so plasma, like we talked about briefly, is a state of matter that starts as a gas and then becomes ionized. And we'll talk about ions and ionization a little later this semester. And it consists of free moving electrons and takes on an electric charge. Yeah.
Wasn't there something that was like, it was like solid, but like folded or something?
Solid, but what?
It's like something like below solid, like.
Okay, yeah, so there are at least two other states of matter, phases of matter, but we don't see them practically ever, and they won't.
Non-Newtonians.
Yeah, something like, yeah, it's not non-Newtonian, it's something like, but yeah, we won't even touch those in this class, because they won't relate to anything we're doing, so. Yeah, we won't be going there, but they do exist. Dudes in the back, zip it. Yeah, you tell them. Okay, changes. Alrighty, so here's your plasma if you add plasma in. So you got your plasma over there, and to go from plasma to gas, it's deionized, and to go from gas to plasma, it's ionized. So when it's ionized and it takes on a charge, it's all those electrons moving. So that's when you see like the negatively charged lightning, right? Okay. But these three others are the ones that you really need to understand. And it's the phase changes between solids, liquids, gases, and the terms in between. So I want you to think for a minute about an example of each of those little black words in there. So sublimation, deposition, vaporization, condensation, melting, freezing. Think of an example for a minute for each of those. So we'll start with an easy one. If you go from a solid to a liquid, it's melting. Somebody give me an example of melting that you might see in your day-to-day life. All right, Xander?
Putting ice in a drink and.
Putting ice in a drink and letting it melt. Okay. How about one that's not ice? Yusuf?
Not ice, never.
Not ice. Do you have one?
I accidentally dropped like a bread thing on my stove that was on and melted it in plastic.
It melted. Okay, plastic melting when it gets hot. Okay, really?
Melts in ice cream.
Ice cream melting. Okay, yeah, that's mostly the water and the milk that's melting, but yeah, it is melting. One more. Kaden.
Butter melting on a piece of bread.
Butter melting. Okay, so in that case, you've got a fat breaking down and melting, and fat will be a solid at certain temperatures and then a liquid at other. How about if you had continued to hold that little copper wire over your flame? Would that have melted?
If it got hot.
If it got hot enough, right? So how about rocks deep in the earth under heat and pressure? Melting, again, going from solid to liquids. How about freezing? Give me an example of freezing, Escher.
Take a big old container of water.
Mhm.
Put it in your.
Water.
And then you come back a few hours later.
And it's frozen. Okay, so Ashley just made a real obvious one. You take a big old container of water and you put it in your freezer and you walk away and you come back some hours later and it's frozen. Let me ask you something. What else would have happened to that water while it's freezing? Who said it? You. Yeah, thanks, Drew. Yeah, it would expand. So here's something about water that's unique. It's not entirely unique, but it's helpful and necessary for life. Water, when it freezes, it gets, when things get cold, they become more and more dense, generally speaking. But water will become more and more dense until it reaches a certain point, and then due to its molecular shape, it will expand. So that's why if you put water in the freezer and walk away from it, it'll come back and look bigger than when you put it in. It's also why you never put a soda in the freezer, because the water in there will expand and the gas in there is under pressure and it will pop open and explode slushy soda all over the inside of your freezer, and you'll come back and it'll look like you're going spelunking because it's like everywhere. Get cave exploring. You'll have stalactites and stalagmites of disgusting soda. Yep. Uh-huh.
There's actually a lot of people taking break open rocks, that way you just go home.
Yes.
The rock and put it under the freezer.
Yes, and we talk in earth science, when we do earth science, we talk about how rocks actually weather more in cold climates, whereas most things are going to weather more when it's warm because heat in general lowers the activation energy for chemical processes, and heat in general can cause, things to melt, and that can change, their physical properties and physical shape or whatever. But rocks, it have cracks in them. If they're up where it's real cold, you get a little crack in a rock and then you get water in it, and the water freezes and expands, and sooner or later that rock just splits wide open. And that is something that happens in cold climates a lot. So that's a good example of freezing, throwing something in the freezer. What's another freezing example that doesn't involve water? Nope.
I was about to say leftovers in the fridge.
Okay, that's primarily the water you're freezing. Okay, Colin.
Deer in headlights.
Deer in headlights, that's always a fun one. Yeah, they do that.
It's 'cause
You
it's
just wish
blind.
they'd run away, but they're blinded and they're not. They don't do it. They freeze. You're right. Who's got another one that doesn't involve water? Chris?
Technically ain't solid or frozen, because it's, you just frozen that.
Yeah, technically it's in its frozen state. Yep. Uh-huh. Yes, PJ.
If that's the case, then soup gelatinizes when it's like.
There you go. Soup that gelatinizes, or Jello. Jello goes from, if you, Drew, Colin, don't talk like that. So Jello goes from liquid to jellyish solid. Uh-huh.
You get frozen pretzels, will occasionally come with frozen cheese.
Okay, frozen cheese. That's mostly water too, but yeah. All right.
Like that scene in Cool Runnings where Sokka's in the cooler, and he just like snaps his hair.
Cool Runnings. Wow, that's a throwback reference. If anybody was gonna make that reference, it would have been you. Well, very well done. James, have you got one? Rocks is a great example. Okay, so think about rocks. When a molten rock comes to the surface, it freezes. You don't think about it that way, but it freezes. When a volcano blows lava up and it hits the ground, it freezes. It's just that its freezing point is really, really, really low. So when something's freezing point is really low, it's going to look just like a solid to you all the time. But at some point, it's a liquid, right? That's what happens. You get something hot enough or cold enough, most things. All right. So, and how about a condensation example? What's an example of condensation? Jordan.
Humidity.
Humidity will condense. So if you ever gotten a nice cold blast, you take it outside on your back deck.
Multiple times
Georgia.
I walk out the window and
Mhm.
my butt's just fog.
And you're like, okay, yeah. And then Annabelle had that problem today because she had her mask on in lab and she's like, I can't see anything. And she walks up to me and like all her goggles are just covered in like a nice layer of condensation. Yep. All right, Lucas.
You on the grass?
Dew on the grass is an example of condensation. Yep.
So you go to McDonald's.
I like this.
Large soda,
Okay.
and then about 5 to 10 minutes later, moisture will start appearing on the outside.
There's your condensation. All right. So then how about vaporization? What's an example of vaporization? Addie, Gabe, do you have one? Can you think of an example of vaporization? Something going from a liquid to a gas?
The lake, like when the sun hits the lake and then it.
Yes. Yes. Okay, perfect answer. All right. So what Addie described was evaporation. Okay, so here's evaporation. Evaporation is a type of vaporization. It's when you lose the water on, or the whatever, the liquid on the surface. So when there's evaporation in the lake, which has occurred, when there's evaporation in the lake, what's happening is it's only those molecules on the top that are changing phase from liquid to gas. What's another kind of vaporization? Okay, Liam.
When you're like making mac and cheese and you're boiling the water.
Boiling. Okay. Boiling is the other big type of vaporization, but boiling doesn't happen just on the surface. It happens throughout the liquid, right? All throughout the liquid. Yes.
Ironing clothes.
Ironing clothes. Oh, when you're using like the steam and yeah, because it's water that you're squirting out, but it gets so hot. So in that case, you got your liquid going to gas and it's happened real quick, but it happens. All right, now we did condensation, vaporization, melting, freezing. Now let's go on to the two trickier ones. Sublimation. CJ.
The snowball thing.
The snowball thing. What's the snowball thing for our new friends?
So.
Okay, so y'all listen, because this is the snowball thing. What is it?
Basically, people on the internet, usually stupid people.
Yeah, okay, fair.
Take a snowball and a lighter,
Mm-hmm.
and they light up the snowball, and then the snowball turns black, and they're like, it's the government putting plastic in the sky.
That's exactly right. It's every stinking year. You watch, mark my word, every year somebody gets snow and they go, look, look, look. So where's the black coming from?
The hood.
It's soot. It's soot. The black is just soot from the butane in the lighter. But the snowball is shrinking while they're heating it up and it's not dripping. It's just not going from solid to liquid to gas. It's skipping liquid and going from solid to gas. It's sublimating. So that's, you will, it'll happen. I promise you, you'll see it when there's a new one every year. I'll look for it this year. When it comes out, I'll show you if I remember to do it. But there's always, and they're always like, oh, the government's putting plastic. No, it's not plastic. It's not plastic. It's not just melting and turning glass. That's not what's happening. Oh my gosh. It's like, we're back to scientific literacy again. Like, are we for real?
How is that even supposed to work?
What's another example of
It's
sublimation?
the AI.
Anybody know? Colin, your hands up. What's another example of sublimation?
Let's see. Dry ice.
Dry ice, great example. That's a good one. All right, so sublimation with dry ice. You don't see it go to the liquid phase. Is liquid what would you guess about liquid carbon dioxide based upon the temperature of dry ice? Where do you think a temperature for liquid carbon dioxide would be? Fairly high, fairly low? What would you imagine?
Real cold.
Yeah, really, real cold. Like real cold. Yeah, for sure. All right, good example. Another example of sublimation is again with snow, but snow drifts, or you build the cutest snowman in the world and you're like, this dude is awesome, man. I love this guy. And you look a couple hours later and he starts to shrivel, but he's not really dripping. He's just kind of shriveling. And then he's sublimating. He's a sublimating snowman. And then frost. Frost does this too. You see frost on the grass. It doesn't usually go wet. It just sort of appears to disappear and it just sublimated. All right, how about deposition? Who can give me an example of deposition? So we're going from a gas to a solid. All right, Asher. Never mind.
I'm not sure which direction this is. It might be sublimation, but I think cryogenic storage has something to do with that.
Yeah, cryogenic storage, that's the same kind of thing. So they've skipped through your liquid. Yeah, they're going, if you're condensing it down, they usually do have to go through a liquid phase to get it from solid to gas, but the other way in reverse, it just goes, to get it from gas to solid, they usually do have to go through a liquid phase, but to get from the solid to gas, it usually just sublimates. Yeah.
Hey,
What?
hey,
Hail. Hail. What about hail?
it goes from a gas.
I said that first.
Yeah, kind of does. Yeah, when it forms, we talked about how hail forms. There's usually some liquid involved because you're up in the clouds and that's fairly condensed. That's why you can see them, right? Okay. Another example, and I mentioned it a minute ago, actually, is frost. So frost doesn't start as dew. It just starts as frost. So it goes from water as gas in the environment, and it gets cold enough that it just kind of collects where it would condense, but it collects as ice instead of collects as water and then turns to ice. So temperature, energy, and state. So liquid evaporates to gas, gas condenses to liquid. Solid melts to liquid, liquid freezes to solid. Solid sublimates to gas, gas deposits to solid. All right. So what do I want here? A property of matter that describes a substance's ability to participate in chemical reactions. Colin.
Reactability.
Reactability is a description of this. Caitlin?
Reacting.
Oh, this is easier. Y'all are making it too complicated. It's just a chemical property. So your chemical property is described, a chemical property. And reactability is a chemical property. So it describes a substance's ability to participate in chemical reactions. What do we call a substance that doesn't participate much, doesn't react much, a non-reactive? What do we call it? Do you know a word?
Noble gases.
Noble gases are example. Yeah. So you may hear the word inert. Means they don't want to play with anybody else. It's a loner, inert, right? We say noble gases are inert. They don't react with stuff. Okay. How about this one? The process by which one or more substances change to produce one or more different substances. All right, Colin.
Chemical reaction.
That's a chemical reaction. There we go. So when you have one or more substances that change to produce one or more different substances. And this year we'll talk about things like limiting reactants and stuff like that. And basically what that means is like you can put a whole bunch of chemicals together, but so much of one is going to be able to react with so much of the other. And sometimes you'll have some left over. So it's basically you can produce 2 new substances, 3 new substances, and there are multiple types of reactions. We'll talk about reactions where you get like 1 replacement, double replacement. There's all kinds of stuff. All right, so what's a substance or a molecule that participates in a chemical reaction called? This is the one you had, ZJ.
Reactant.
That's your reactant. So if it's playing the game, it's a reactant, okay? And what is it if it forms from a reaction? All right, Lucas. There you go. It's a product. So your reactants on your chemical reaction are on your left, and your products are on your right. So signs of a chemical reaction, formation of a new substance. So those of you who were here last year, you've already seen some of these. So let's give some of our newer friends a chance to answer some of these. So these are signs that a chemical reaction has taken place. All right. So what do you think this might represent? It's a sign that a chemical reaction. All right, Ryland. Color change. Exactly. Color change. A color change. Shh, in the back. Y'all. If I got to talk to you next week, I'm gonna move you around. Color change is a sign of a chemical reaction. Now we'll see color changes this year with indicators. We'll use acid and base indicators, and then we'll also just do some reactions that are going to cause a color change. So that's a great example. Can you think of an example of a color change that you might see in nature? That's an example of a chemical reaction. Katie?
Chameleons.
Chameleons do it. That's a great example. What else? Jordan?
Grass changing with.
Yeah, grass or leaves. Yeah, you're getting at it. Yes. So when your leaves change color in the fall, it's an example of a chemical reaction there's a chemical reaction going on in there. And it has to do actually with certain pigments becoming less and less prevalent within the leaf. Andrew?
Rainbows.
Rainbows. Okay, so rainbows is interesting. So rainbows are it's a physical phenomenon, and it has to do with refraction. So basically with a rainbow, you've got, where is your name? There it is. Basically with a rainbow, what you've got is you've got light coming through little drops of water, and those little drops of water act like prisms, and they change the full spectrum of electromagnetic energy that's coming through that looks like white light to us. It splits that white light into different wavelengths so you can see the colors. So that was not actually a chemical reaction, but like a manifestation of a physical process, but it's really cool. Okay, Drew.
Lightning striking the tree.
And what happens to the tree?
It turn different, it could just be darker.
Yeah, it'll get burned. It'll get black. So yeah, there you go. All right. Good. Where is you? All right, how about this next one here? What do you suppose this represents? Gabe?
Smell.
Yeah, production of an odor. All right, so this is another example of a chemical change, production of an odor. You can give me an example. Oh, are you going to give me an example, Colin? You look like you're good.
Except for the last one.
Oh.
I went for the last one.
It's not really a color change, but bioluminescence.
Bioluminescence is definitely chemical. That's production of light, but we'll get there. Yep. All right, Kaden, what's an example of production of odor?
Food going bad.
Food going bad is a great example. What was in your email last week about making a personal resolution? What was that about, Ridley?
Don't be a stinky kid.
Don't be the stinky kid. Why do we stink? What makes us stinky, Caitlin?
Hormones.
Your hormones. Yeah, absolutely. That's true. So you have microbes that live on you. They're not bad. You need them. They're little bacteria and whatnot that live on your skin, live in your body, on your body, in your body. They're necessary for function. If you didn't have microbes in your gut, you'd be sick. And for example, termites still can't digest cellulose, which is the component of the cell wall in a plant. So cellulose, we call it fiber in our diet. We can't digest it either, but termites can't digest it, but all they eat is wood. But a microbe in their gut can, which is how they eat wood and actually survive. So you got microbes on your body and you get dirty and sweaty and you've got skin cells dying all the time. And you've got these nice, wet, warm armpits and everything else that's like that. And those little microbes just eat. Basically, they're burping and farting out the smell. So when you smell, you are smelling like microbe farts. So I want you to keep that in mind. When you're walking in here and I'm going, oh, somebody didn't do a smell fee, you are a walking fart factory. So let's fix that for the future, right? We can do that. We all agree? We all agree? Yes. Nobody wants to be that. Do they? Do you want to be that? Anybody want to? No, let's not do that, right? So production of an odor, and like Caden said, when fruit starts to rot, this is also how a lot of animals will find their food, scavengers in particular. They're looking for the gases that are produced when living organisms, animals in particular, start to decompose. That chemical odor is a sign to them that there's like a dead deer on the side of the road. So I'm a turkey vulture and I'm going to take my unattractive bald head and stick it in there and have a great old meal. Yeah. Lucas, anything else?
Can I do it, one to the previous thing?
You have another color change? What was it?
A sunset,
A what?
a sunset.
A lot of that's refraction too, but depending on the chemical in the air, there can be some reactivity, but usually it has to do with how the light is behaving in that case. But yeah,
James all the time is a production of odor.
James, you've been called out.
My brother's whole.
Mm-hmm. Coyote's room? It's bad.
It's bad.
Oh my. Okay, Caden, you got one more?
For color change.
Uh-huh.
If you throw copper oxide in a lit fire, it should change its color.
Yeah, almost anything with copper, if you throw it in a fire. We have pure copper and we have copper acetate, monohydrate. And we have a couple other chemicals that if you put them in fire, they will change color. One of the labs we will do this year is looking at the spectrum produced by certain chemicals when they are put in fire. And it's fun because different chemicals produce different colors across the board. And it's really, really neat. And one of my favorite college professors was this adorable man named Bonsi Kalra. I loved Bonsi Kalra. He wanted us all to call him Bonsi, not Dr. Kalra. But Bonsi was this hilarious little man. And he liked that lab so much. It wasn't even a lab. It was just an experiment for him. He always had a Bunsen burner on his teacher desk. And in the middle of, we'd be talking about something, and he'd just start throwing chemicals on the burner. And, you know, the burner flame kept changing color. There were chemicals all over, like powdered and granulated chemicals all over the desk. And he, in the middle of class one time, he goes, one time I did this and I caught my shoe on fire. And he looks around and we're all like, what are you doing? But his favorite was strontium, which produces this bright, like almost hot pink red. And it's a bright, bright color. And he would just do it. He'd just be sitting there talking to you and he'd just like throw chemicals on flames. He was a great guy. All right. So how about this one? What's this? Anybody know what this might represent? Something's happening. Liam.
Precipitation.
There you go. Formation of a precipitate. Okay. So a precipitate is when you get a solid forming in solution. And there's a great chemical term for this. And I love this. There's some fun words in chemistry. This isn't even like a big word, but it's a great term. So when you form a precipitate, they refer to it as crashing out of solution. How fun is that? It'll be like, oh, and it crashed out of solution. It just sort of looks like milky or whatever it looks like at the moment, but crashed out of solution is the term we use. That's great. That's a great one. That's fun. So precipitate, this one's a little harder to think like, what's an example? Can you think of an example?
Food coloring?
Food coloring, no, it doesn't form a solid when you put it in. It just changes the color of the water. Do you know, James?
You were to salt.
Salt and water, so
Settle back down.
so that's sediment. So that's why this one's harder. So what's going on there is you've got some that's behaving like sediment, and usually because it's super saturated and it can't take any more salt, so that salt just sort of falls to the bottom because it's heavy. But there wasn't a chemical change, they're dissolved. Okay, Caden, do you know one?
It might not be a precipitate, but if you have water and oil in a cup. And
Yeah.
then you throw some soap in there, it breaks the surface.
It does.
And-
So yeah, so that's not a precipitate either, but it's a really good example of how so that's taking advantage of the fact that water is a bipolar molecule, meaning it has a slightly positive end and a slightly negative end. And in that case, your dish soap acts as a surfactant. So what it does is it's attracted to one end of that water molecule, and the other end is attracted to the fat. So it pulls the fat one way and it pulls the water the other way, or the oil, and it can help emulsify or separate it. There's also these cool things. Anybody ever, especially ladies, anybody ever heard of micellar water? Yeah, you heard of micellar water? Do you know what it is? I use it to take my makeup off. So what it is it's water containing these things called micelles. Oops, let me flick that back on. Sometimes it happens. So my cells are these really cool little spherical structures, little microscopic spherical structures that have the hydrophilic hydrophobic thing going on. So like water, don't like water. And they have like, it has like a heads and tails, and the heads make the outside of the sphere and the tails are on the inside of the sphere. So basically they act like little cells. No, cells is the wrong word. Cells, I'm thinking like the kind that you would capture something in, not like the smallest unit of life cells. But they will grab the little molecules of oil, like from your makeup or from your skin, and suck them inside and keep them captured. Hold on a second. He's leaving for, I don't know. You leaving? Bye. Love you. Have a good trip. See you. Bye. All right. Getting on an airplane. Heading out. Where are you going?
Denver.
Okay, bye. I don't even know. It's just leaving. When are you back? Okay, bye. This is my life. I don't know. He's gone. He's gone. Denver. Okay. So do you have an example here, or what do you want to add?
Blood clots.
Blood clots. Okay, so blood clots are real involved. There's a lot going on there. In blood clots, you've got platelets that are exploding and they produce something called fibrin,
Positive.
comes together, it joins things. So it's not really a precipitate, but Drew?
Just an idea, like when you put milk inside of a cup and then you put it inside the microwave for like 3 minutes, there's like a little formation of those.
Yeah, so that has to do with you. So what you're doing there is you're breaking down some of those you're denaturing the molecules using heat, and then you've got your fat separating out of your solution that's otherwise homogeneous, but now it's no longer homogeneous. So real life examples of this are harder to see, but we'll do this in lab multiple times. There will be times in lab where you'll have a test tube full of one nice clear solution, and you drop another clear solution in it, and this milky stuff just suddenly forms, and you're getting a precipitate then. So you will see it. It'll happen. All right. How about this? What do you think this one represents? Those are bubbles, if that helps anybody. PJ. Gas. Yeah, production of a gas or evolution of a gas. So we get gas a lot with chemical reactions. Sometimes you get gas when things dissolve and produce a gas, and other times you get gas. Where's a good example? What's an example of a gas that can be produced? Colin?
When you put like, one of those like tablet, like vitamin tablets in water.
Yes. Those start to dissolve, break down, and they produce a gas, Drew. Marijuana? Where you get that? Well, or any, that's an interesting answer. Let's not do that. Yeah. But really what you're doing there is that's combustion. Yeah. And you're breaking down. In that case, what you're doing is you're breaking it down, and you're consuming lots of things. You're consuming the carbon that's broken down. You're consuming all of the carbon dioxide and room air and oxygen that you're breathing in, but you're also getting people that do that. They're looking for the THC and the CBD breakdown, which are two different chemicals. Yes.
Heating up mercury and separating it into oxygen.
There you go.
and mercury.
You're going to be dangerous this year, I think. Secret lab.
I was
going to say, do you have a lair that I don't know about? Because that would be cool. All right. So how about when you put baking soda and vinegar together? What do you get? Get carbon dioxide, right? Yeah. So yes, you can get gas that way too. So there are certain chemicals you can put together and just produces a gas. Yes. Digestion. Yes. There's a lot of gas production and digestion. This is true. All right. Let's look at this next one. Did it go two, or did you just go one? No. All right. What's this one, do you suppose? What are we representing here? Jordan?
Temperature.
Temperature changes. All right. Who has an example of a temperature change that's due to a chemical reaction? Lucas? Guys, shh. Lucas? We'll come back to it. Do you know, Asher?
Elephant toothpaste.
Elephant toothpaste does get hot. If anybody's ever done that, kaboom. Yeah, it does get warm. That's a good example. What's another one, Drew?
Like the packs that they have and that, like little ice packs where they're like normal. You
Yes, those are great examples. So the ice packs that you use for like sports injuries or whatever, they feel slushy when you shake them around. That's an example of something that gets cold. What do you think, Ridley?
There's something you use it to make soap. You put
Okay.
it in certain wrong things like water, it
Uh-huh.
can explode and
Ooh.
get really, really, really hot.
Oh,
So be very careful with it.
okay. Yep. There are all kinds of things like that. Uh-huh. La, 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 la. Okay, Liam?
You know, like whoever back there was saying with the ice packs, like the hand warmer.
There you go. That's the
Like,
other one.
when you, like shake them up and they get warm.
Yes, so that's the other another really clear example. So hand warmers will get warm, ice packs will get cold, right? Oh boy, James. Fire, yeah, okay, that's combustion. That's combustion, but yep, okay. And Colin.
Nuclear explosion.
There's that. Okay, and how about Andrew, you give me the last one on this one. Thunder. Okay, so thunder is due to a rapid change in temperature. But the rapid change in temperature is coming from the plasma created by the lightning usually, right? So you have a rapid change in temperature of the gas, which it rapidly expands. And when it rapidly expands, you hear the impact of what kind of wave is produced? What kind of wave is a sound wave? Do you know, Kaden? What kind of wave?
Okay, I wasn't expecting for it to be.
Oh, no. What kind of wave is a sound wave? Oh, come on, y'all know? Asher? Yes, it's a longitudinal wave. It goes like this, not like this, right? Boom, 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 boom. And that's what you're hearing is literally air smacking into air. All right, what's this one representing? All right, Xander.
Right?
Yes, production of light. Okay, obviously, glow sticks. Great example. Bend them, snap them, shake them around. You got light. What's another example of a chemical change that produces light? Can we think of any others, Liam?
Fireflies.
Fireflies. There you go.
Shrimp thingy.
Yeah.
And a little shrimp thing.
And a little, yes. Kaden, you got another?
I have two, anglerfish and putting sodium oxide in water.
Yeah, okay, there you go. Those are great. Those are all great examples. You got one more?
Like a lantern shark or whatever.
Yeah, all of those animals that are bioluminescent, James. Like, yeah, there's definitely some chemical activity going on in there. And Drew?
Nuclear fusion.
Okay, there you y'all are fun back there, man. All right, now, how about this one? What's this representing? It's not light.
Explosions.
Yeah,
Prediction.
go ahead, Lucas.
Production sound.
Sound is the one I'm looking for. Yes. Okay. So this is exactly what Andrew just said when he talked about thunder. So thunder is a clue that there has been a chemical reaction because now you've got sound. Okay. There will be an opportunity this year. Yeah, this year. You're going to produce some oxygen and you're going to do it by using hydrolysis with water. So you're going to take water and you're going to break the hydrogen and oxygen down. You're going to split them up and you're going to produce and separate hydrogen and oxygen from water.
Ooh.
And when you test to see if it's really oxygen, it'll be in a little test tube and you'll take the top off the test tube real quick and you'll have a match that you will have lit and then blown out. So it's still, guys, it's still glowing, but it's no longer on fire. You get the little match and you open the little test tube and it will go pop, nice and loud because you had an instant of combustion in the presence of the oxygen that was in the tube. And it's great fun. It makes this like little whistly pop sound. It's really kind of fun. Drew.
V8 engine.
A V8. There's a lot of reaction going on in there. Yep, a lot. A lot of combustion. A good old internal combustion engine. Caden?
Ring caps and a pop gun.
Ring cap. Oh, yes. Anybody ever had a cap gun?
Yeah.
Oh, that smell.
Those are fun.
You'll never forget the smell, right? It's the smell of a cap gun is like forever ingrained in my head from my boys having them and from playing with them as a kid myself. All right, one more. Yes. Fireworks in the picture. Yep, there we go. Fireworks are a great example. Now, see how these are, oh, Andrew. Okay, what?
A pistol.
Okay.
Yes.
There's a definite chemical reaction that happens there. Some more combustion, basically. Yep. So these are different colors, right? And so that's what we're going to see in the lab when we do flame test. You'll see the different colors and it'll be the kind of thing where at the back, where when you go to a fireworks display in the future, you'll go, oh, copper, lithium, barium. You'll know what it is just by the color. You'll know from now on what's being blown up above your head. You'll know. Okay, Caitlin.
I made a reference from earlier.
Yeah.
Colin, I'll do you one better. Why is
What?
What'd she say?
I'll do you one better. Why is more?
Say something?
James, I'll do you one better.
Ah, there we go. All right, Drew, do you have something to add?
What color does copper make?
Copper makes a nice blue-green color.
Blue. I said green.
It's kind of a blue-green. It's kind of right in the middle. It's greenish, but it has it's so like barium is like a yellow-green and copper is like a blue-green, but it's pretty good.
Blue.
It's really right. It's kind of tealish. It leans more green, I think, but it's pretty blue. But it depends too. Like it depends on what it's with, pure copper versus like there've been times when I've had leftover copper acetate, which is nice blue powder, and just I've had a little bit left and taken it to my bonfire pit just for fun and watch the flames change color, and it's really cool. It's like Harry Potter flames. It's neat. Yeah.
Andrew, I'll do you one better. Nuclear explosion.
Nuclear explosion. All right, and then this last one would be anybody?
Ectoplasma.
Plasma, yeah. So this one is absorption or release of electrical activity, which is a thing for sure. Batteries are stored chemical energy. And when you're releasing the electricity from them, it's because there's a reaction going on. And you can see this, well, I'll come back to that later. Yeah.
Lemon batteries.
What is it? Lithium batteries? Yeah. Mm-hmm.
Lemon battery.
Oh, lemon batteries. Yeah, yeah. You can make a lemon battery or potato battery, Drew.
Electricity within your body and your muscles.
Yes, absolutely. Within your body is chemical reaction on top of chemical reaction. Yep, Caitlin.
Power lines?
Power lines, they're transporting it. It's more transporting it than changing it, but chances are whatever you're plugging it into, there may be something going on. James. Touch screens, there you go. Lucas. Yes, photosynthesis is a great example. Okay. Describing matter, let's describe. All right, what is anything that has mass and takes up space? Andrew. Okay, mass is this, the volume is, volume is how much space something takes up. Do you know what it is when it is anything that has mass and takes up space? Do we know what it is?
Look at the
We're
picture.
close, yeah, the picture's a hint. Anybody want to take a guess? That's matter. So what we're looking at is matter. So mater's made of matter. Matter made up matter. Matter made matter. Yep. Yep, Matt.
Oh my.
I'm made of matter. Yep. He's made of matter. We're all made of matter, right? There's matter everywhere. Matter is anything that has mass and takes up space. Give me an example. One example. Oh, Gabe, you can do this one for me. Give me one example of matter in this room that you can see.
You?
Yeah, that'll work. I'm made of matter. Yeah, yeah. Okay. Yep. The dog, glass, the wall. All right. Somebody give me an example of matter in this room that you can't see.
Air.
And Drew. Air. Yeah, there you go. So don't forget the air. It's real easy to forget that air exists, but it's, kind of important. All right. What is the measure of the amount of matter in an object? Xander. Think about it. How much matter something is made of is its mass. There you go. All right. And what's the measure of gravity on mass, Jordan? Weight. Will my weight change if I'm on the moon? Does the amount of mass I have change if I'm on the moon? No. What's the amount of space an object occupies? All right, Lucas. That's its volume. All right. What is the ratio of a substance's mass to its volume? Which means it's a division problem, mass over volume. Asher? There you go. All right. So its density is its mass over volume. All right. You did this in lab today, right? What was the density of water? Who had it? James, what was it? 1 gram per milliliter, right? And we use water as like a reference point for a lot of other things when it comes to density in general, okay? Mass divided by volume is density. All right, how about, go. Something that has magnitude, size, or amount. What is this? Do we know? Oh, Jordan, do you know? Vector. Hey, yeah.
Oh yeah.
Right. A vector has magnitude and what? Magnitude and direction, right? Okay. Magnitude, size, or amount is going to be quantity. So yeah, that's it. You don't think about this word. You probably use it every day and don't think about what it means, right?
You're a bit off.
There you go. But okay, so how many eggs are in a quantity of a dozen? 12. How about a baker's dozen? 13, right, okay, so dudes at the back. All right. A quantity adopted as a standard of measure is what? Caden, do you know?
The system of measurement.
This one's easier. So this one's unit. So a quantity that's adopted as a standard of measure. Okay, a foot. Let's think about a foot. What does that mean? It's 12 inches, but where did it come from? Do you know? Anybody know? Do you know?
On your leg.
Do you know? Yusuf, do you know?
Someone's foot.
Someone's foot. Yeah.
They measured a carrot.
You measured a carrot. So the legend I've always heard, not sure how completely historically accurate it is these standards of measurement were whoever the monarch was at the time, and his foot became the foot.
Yeah, that's right.
Yeah, right. So there's your foot, your yard, your acre, your centimeter. What's a centimeter? How do we determine what a centimeter is? It becomes the unit. Anything can be your unit. You can measure, guys, you can measure by pencils. You can measure by apples. You can measure by PJs. You've been lined PJ up 4 times. I'm sorry.
I've been used
understand
as a unit of measurement before.
I know, me too. We're not gonna go far. We're not gonna go far, but anything can be a unit. Liam,
I've been used as a unit of measurement before.
have you?
If I have.
At practice or?
No, is that something for a book that I liked?
Okay, a unit of measurement was your book that you liked.
No,
In the book.
I was using it.
You were used as, yes.
If you have 4 fingers on each hand, the base is 8 instead of 10.
That's a good point. See, and isn't that weird? All of our base 10 stuff, this comes from this, right? Like if we all were born with 4 fingers, then our base would be 8, not 10, and our whole world would be very different conceptually. PJ.
You can 2 things.
Mhm.
I know this was Bob's Bookers episode. Pussies are measured in hands.
Mm-hmm. Mm-hmm.
And you can count higher than 10 on your fingers if you like use the little lines. You can go
Yep.
to 24.
Yep. Mm-hmm.
1, 2, 3,
Yep, horses are measured in hands. You say, how many hands is this horse? It's always interesting to me, measured in hands. Whose hands? Not my hand. But there is a standard. I think a hand is like, isn't a hand like 6 1/4? It's something very random. Again, whatever unit. So in chemistry, you often need to convert a measurement from one unit to another. So one way of doing this is to use what, which is a ratio of 2 units that express a measurement of the same quantity. Do we know? Okay, this is a conversion factor. All right, now we're gonna get minorly mathy here, but you'll survive it, okay? All right, so how do we use conversion factor? Now I'm gonna tell you, you're gonna look at some of this and go, this is dumb. Why am I doing these simple problems with all these unnecessary fractions / ratios? Okay, you'll see. I promise you, you'll see. All right, so I will pass these. And if you want these, you can use these or you can use paper. So we're gonna do a couple of problems. If you would like these, you may work on these.
Not really gonna, but like,
Yeah, we're gonna put a stack of them here. Yep, and I'm gonna take a stack of them.
Oh, I understand what's going on.
Yes.
Imagine.
Thank you.
Abracadabra.
Go work out this problem. And try to think of what conversion factor would you use? We're going from centimeters to meters. So what conversion factor would you use? We're gonna be a little more specific than that. And just wait. Give everybody a minute.
One centimeter. 1 meter is 100 centimeters. So that would mean.
All right, give everybody a minute. Okay, today's the day you might leave here hating me because you might go, oh no. No worries, you're all gonna get really good at this. What's the most basic way? Yusuf, what did you say?
0.01 or times 1 by 100 or
Yeah.
divide by
You think, okay, I just did, yeah, just multiply this by 100 and I get my meters, right? Okay, but I'm gonna show you.
Good, divide by 100.
Okay, so here's what we're gonna do though. Here's how we're gonna write these, and you'll see why in a minute, so bear with me. So you wanna know 277 centimeters equals some kind of meters, right? So these are your conversion factors. You can use centimeters over meters or meters over centimeters. Does everyone agree that 100 centimeters over 1 meter is equal to 1? Yes. Does everyone agree that 1 meter over 100 centimeters is equal to 1?
Yes.
Okay, what are we trying to get? What do we want? We want meters. So which one of these has meters on the top? The second one. Okay, so that's going to be our choice. That's what we use. Now, you have to write probably more than you're used to because you go, oh, I can do this in my head. But no, because you'll see why in a minute, okay? So you're going to take your little distance here, your 277 centimeters, and you're going to multiply it using this conversion factor. When you multiply it using this conversion factor, your centimeters are now gone, right? So now you get 277 times 1 meter over 100. So you're going to be left with meters, right? Your centimeters are gone. Canceling units. Are you paying attention back there, Drew? Colin? So then you get this, and there's your answer, 2.77 meters. Did everybody get, or most of you get, there you go, 2.77 meters. And you just went, oh, I can do that, 2.77 meters. All right, the next problem, try it like this by writing it out and putting the conversion factor in. So how do you convert 68.71 kiloliters to liters? So again, that's what you're aiming for, and your two conversion factors are going to be here. So which one? We want liters on top, so which one do we use? The first one. Okay, so set it up. Take some time, be neat. While y'all do that, I'm gonna pick up these extra clipboards and put them on the counter, and you can put yours back when you walk out. You have to kind of offset these, flip them around so they fit. All right, so our first step, after we've selected, guys in the back, zip, selected our conversion factor, we're going to multiply it like this. So what do we get rid of here? Kiloliters, they're gone. So what do we multiply by? 1,000 over 1, which is multiplying by 1,000. Is this what we got? Easy peasy, right? You're like, this isn't hard. I'm not afraid of chemistry. I'm not afraid of chemistry, man. Let's see. All right. So for some of you, you're probably like, this is stupid. Why am I doing this? Okay. Yes, it's just base 10. Can't I just do it in my head? Why go through all this trouble? Okay, well, this is what it's going to look like shortly. All right, it won't be long before we're here. Do not panic. This is not the end of the world. So if you have mass in grams and you need atoms, y'all.
No.
I got a certain amount of math. How many atoms are in here? Yes, you can calculate that, which is pretty amazing when you think about it.
Can I not?
So this question was, how many oxygen atoms are there in 200 grams of oxygen? So you get 200 grams of oxygen, how many atoms are there?
Plenty.
So what we did here is you have 200 grams. So what we're going to use is this conversion factor, which is moles. And that's a fun number. Does anybody know what that number is called? It has a name. Do you know? That is Avogadro's number. Yeah, 6.02 times 10 to the 23rd. Memorize that one. There aren't a whole lot of numbers and conversion factors that need straight up memorizing. That one does. 6.02 times 10 to the 23rd. Yes.
The reason that I remember that because that's how I lost $5 from a bet with my brother.
He was right. And you were wrong. You were wrong. I didn't think you were ever wrong.
He said, I'm gonna ask you a question on sentence. If you can answer it, I'll give you 5 points. If you can't answer it, you give me 5 points.
Okay. So this really isn't crazy. Like if I said to you 10 minutes ago, before any of this even appeared on your radar, and I said, how would you tell me how many atoms are in 200 grams of oxygen? You would have probably gone, carrot? Because what? But you can do it. You can actually do it. You can take your 200 grams and you know that you've got your 6.02 times 10 to the 23rd. Now you're going to need, what is a 16? What is 1 over 16? Anybody know what that is? That's molar mass. We're going to learn that too.
No.
That's so fun.
No. Come
Use your molar mass, and then you end up with 12.5 moles. Well, moles, how many atoms are in 12.5 moles of oxygen? Well, you're going to take your number for moles, which is your Avogadro's number, and then you get this nice big, there's your scientific notation, 75.25 times 10 to the 23rd. Anybody want to write that number out with zeros and play with it?
No.
Oh, no, you don't, right? Much easier to
No.
play with it when it looks like that. Much easier. So this is all stuff we're going to be learning, and it's not, don't panic over it. Look, here's the deal.
Just leave it alone.
I have full transparency. Drew, exhibit. Full transparency. If you feel brave enough to do so, you don't have to. But if you have a learning disability, raise your hand. Anybody else want to join me? There we go. Hello. Anybody care to share? I'll go first. Mine's dyscalculia. Does anybody know what dyscalculia is? What's dyscalculia? Anybody want to guess?
Things in your head.
Can't do math, y'all. But somehow I got a degree in science, and I am terrible at math. I can understand it while it's going on. Ask me 10 minutes later, my retention is terrible. I will throughout this year repeatedly do basic arithmetic wrong. Very wrong. Not my fault. I've done everything I can do to make it better. It's not going to get better. It's like dyslexia kind of, but for numbers. And I'm real bad at it. But if I can get a degree, I had to go all the way through organic chemistry. That was the most math I did. Organic chemistry is a lot of math, and it's a lot of, it's a tough chem. It's a tough chem. I look back on it and think that I barely passed, but I got like a B-. But I really feel like I barely passed because that's how hard it was for me. Like I was like, oh my God, every day. And there was a one professor I had who wasn't just like the warmest, most wonderful person. She was not warm nor wonderful. And she confused me with another girl for a whole year. But labs were great fun. Lots of making colors, lots of chromatography and spectrometry and fun stuff like that. So yeah, if I can do this, you can do this. Seriously, if I can do this, you can do this. When they do certain learning disabilities, when they diagnose them, they're looking for a greater than 15-point gap between your IQ, which is your potential, and your performance. So 15 points will get you a, yeah, that's a disability. Mine's like 35. It's a big. So yeah, so if I can do it, you can do it. I will probably screw it up a lot. But this is also why you're going to see most of my calculations done on slides like this, because if I try and do it live, I'm going to mess it up and confuse everybody, and it's not good for anybody. All right. So I want you to establish a habit of working in a neat and organized fashion using conversion factors. They're your friends. I know they look scary, but they're your friends. Get used to it and don't try and skip ahead. I know a lot of people are like, I got it in my head. And they just don't. Just write it down. Because I'll tell you why. You'll get home and look at your lab and you'll be like, how'd I get that number? If you didn't write down how you got it, you're not going to remember, because there's going to be a lot of data in these labs. A lot of data. And the data can be very specific numbers with many decimals. So you're going to need to write everything down and be very specific. So we did those to try. Here's a couple others. We'll do a couple more. Get everybody to try one or two more. So an automobile uses 0.05 milliliters of oil for each kilometer it's driven. how much oil in liters is consumed if the automobile is driven 20,000 miles. We're gonna hope we don't burn oil like this, but some cars will. If you can't figure this out, don't panic. It's just take a stab at it. See how you do.
Oh.
Give you a few minutes. See if you can do it. This is just to see if you can do it. And yes, use calculators. By all means, use calculators. But I prefer if you use them for saying things like, hey Siri, what's 243 divided by 12.6? Rather than solve my whole problem for me, right? And some of these, she is not going to be able to solve these problems for you. Now, AI probably would, but let's not do that. Like, I'm sure if you ask AI how many atoms are in 200 grams of oxygen, it'll tell you right away.
On the topic of AI, I had to do this like AI thing of like how to use it smartly for doing numbers.
Yeah?
Yeah.
Was it helpful?
Kind of.
Was it for a GE, like dual enrollment or?
Yeah, it was for doing enrollment.
Excellent.
No, my teacher of course says no AI at all.
No AI at all.
You
Yep.
get a 0.
Yep. No AI at all. Yep. All right. So this one, if you worked it out, should have gotten about a liter.
Yes.
Yep. Okay. Some of you did. If you didn't, don't panic. Okay. Here's another one. Becky drinks 8 300 milliliter glasses of water each day. How many liters of water will Becky consume in a year? What is the mass of this yearly volume of water? So you have to assume it's a regular year. 365 days.
Instead of 365 days and, instead of and.
Oh yeah, you're right. You got one. So you're gonna want to write it down. Put it over there. That's how we're gonna do it this year. You gotta write them down because I will forget them otherwise. Yep.
Oh.
Takes 2 seconds. Take one of the spare pieces of paper. Write it down. Say where you found it and what it was, and put it in the folder over there.
This was the first one that I had to use a calculator to figure out
Yeah.
something.
Yeah.
I don't use my brain properly.
My brain is barely there.
My brain doesn't.
Some days. Well, and y'all will probably get to observe the fun phenomenon of lupus in action sometime this year. And it probably won't be the limping around or inability to move that kicks in. It'll be when my brain just stops functioning and I like sound like a crazy person.
My brain does not brain.
It's real fun. But, you know, my body's constantly trying to kill itself. So sometimes it tries to kill my brain and then my brain goes, and it's like a short circuit. It's crazy. All right. So this one should have gotten about 876 kilograms of water or 0.876 liters per year. So you did. How's matter classified? We're going to roll through these real quick. So this is just your terminology. A substance that cannot be separated or broken down into simple substances, that's your element. All atoms of an element have the same atomic number. Smallest unit of an element that maintains the chemical properties of that element is your atom. Okay? Substance made up of atoms of 2 or more different elements, that's going to be your compound. And a sample of matter, either single element or single compound that has definite chemical and physical properties, is a pure substance. Mixtures real quick. We're going to do these real quick. Mixture is a substance made by combining 2 or more different materials in such a way that no chemical reaction occurs. Mixture can usually be separated back to its original components. We have types. We have homogeneous or homogeneous, some people will say. And these are particles that are evenly distributed and not easily separated. Solutions would fall into this category. And these are things like suspensions and colloids as well. And then you have heterogeneous or heterogeneous particles that are easily separated, like in this berry salad. I'm going to come back to that in a minute. Go through these real quick. So what did we learn? Describe a way in which chemistry is part of your daily life. Describe the characteristics of 3 common states of matter. We've already talked about this and this. Describe physical and chemical changes. We did these. And describe 8 observations that denote. We did this. Okay, now distinguish between characteristics of matter. We did this. Identify and describe physical properties, including density. Identify chemical properties. Look at all we did today. All this. Distinguish between elements and compounds. Distinguish between pure substances and mixtures. Classify mixtures as homogeneous or heterogeneous. Explain the difference between mixtures and compounds. See you next week. Now, you will have, in the future, there will be some, when you have worksheets and stuff as part of your binder where it's like fill in the blank answers, sometimes what I'm going to do is put the whole sheet up there, and you can take that whole sheet and all of your answers will be up there and you can look and check it at the end of your lesson. I'll put this on as our closing. So how was aspirin discovered? And after this video, when you leave, take your clipboard and your marker and return it over there on the counter. But here is how was aspirin discovered. This was in your book under the biology section. Oh, what happened? Hold on. Oh, I know why. Because it's doing this stupid thing. Oops. Maybe not. Maybe it's gonna fail on me. Oh, it's swapped out. Alexa, turn on Media Center. Gonna fail on me entirely now. There it is.
4,000 years ago, the ancient Sumerians made a surprising discovery. If they scraped the bark off a particular kind of tree and ate it, their pain disappeared. Little did they know that what they found was destined to influence the future course of medicine. What the Sumerians had discovered was a precursor to the medicine known today as aspirin. Aspirin's active ingredient is found commonly
Guys in the back, some people are watching, so keep quiet.
Which is how it came to infuse the medical traditions of Sumer, ancient Egypt, ancient Greece, and other cultures. Around 400 BC, Hippocrates, thought of as the father of modern medicine, first recommended chewing willow bark for pain relief and making willow leaf tea to ease the pain of childbirth. But it took over 2,000 years for us to comprehensively investigate its potential. In the mid-18th century, an Englishman named Edward Stone ran 5 years of experiments showing that willow bark crushed into a powder and eaten could cure a fever. It took nearly another 70 years for a German pharmacist, Johann Buchner, to finally identify and purify the substance that made all this possible, a compound called salicin. By then, doctors were routinely using willow bark and other salicin-rich plants like the herb meadowsweet to ease pain, fever, and inflammation. But identifying the exact compound suddenly opened up the possibility of manipulating its form. In 1853, a French chemist managed to chemically synthesize the compound, creating a substance called acetylsalicylic acid. Then, in 1897, the pharmaceutical company Bayer found a new method and began marketing the compound as a pain reliever called aspirin. This was widely recognized as one of the first synthetic pharmaceutical drugs. Originally, aspirin was just Bayer's brand name, A for acetyl, and spur for meadowsweet, whose botanical name is Spirea ulmaria. Soon, aspirin became synonymous with acetylsalicylic acid. As its influence grew, aspirin was found to ease not just pain, but also many inflammation-related problems, like rheumatoid arthritis, pericarditis, which inflames the fluid-filled sac around the heart, and Kawasaki disease, where blood vessels become inflamed. Yet, despite aspirin's medical value, at this point, scientists still didn't actually know how it worked. In the 1960s and 70s, Swedish and British scientists changed that. They showed that the drug interrupts the production of certain chemicals called prostaglandins, which control the transmission of pain sensations and inflammation. In 1982, that discovery won the researchers a Nobel Prize in medicine. Over time, research has also uncovered aspirin's risks. Overconsumption can cause bleeding in the intestines and the brain. It can also trigger Ray's syndrome, a rare but often fatal illness that affects the brain and liver in children with an infection. And in the late 20th century, aspirin's success had been overshadowed by newer painkillers with fewer side effects, like acetaminophen and ibuprofen. But in the 1980s, further discoveries about aspirin's benefits revived interest in it. In fact, the 1982 Nobel Prize winners also demonstrated that aspirin slows production of thromboxanes, chemicals that cause clumping of platelets, which in turn form blood clots. A landmark clinical trial showed that aspirin reduced heart attack risk by 44% in participants who took the drug. Today, we prescribe it to people at risk of heart attack or stroke because it cuts the likelihood of clots forming in the arteries that supply the heart and brain. Even more intriguingly, there's a growing body of research that suggests aspirin reduces the risk of getting and dying from cancer, especially colorectal cancer. This might be due to aspirin's antiplatelet effects. By reducing platelet activity, aspirin may decrease the levels of a certain protein that helps cancer cells spread. These discoveries have transformed aspirin from a mere pain reliever to a potentially life-saving treatment. Today, we consume about 100 billion aspirin tablets each year, and researchers continue searching for new applications. Already, aspirin's versatility has transformed modern medicine, which is astounding considering its humble beginnings in a scraping of willow bark. TED-Ed is a nonprofit. If you value our work, please consider supporting it on patreon.com/TED-Ed.
I think it's down there.
PJ, you have coins. PJ.
No. Sarah. Catch you later.
PJ, you have coins.
Okay.
You have coins.
They're mine, I'm a monster.
They're mine now.
Just one amongst my people. My empire. Huh?
Good.
Coming to Ogden? Oh, I think he's gone down to my mom. He's like, done with y'all for the day. I'm gonna go hang out down here. Where it's quiet. Alexa, turn the television off. It's not bad, I swear. Really not that bad. Yeah, if I can do it, you can do it, math.
You're better at math than I am.
I don't know about that.
I do, you did pre-cal, college, right?
I failed it. Yeah.
Failed it, right?
No, I failed it.
Didn't have to take it yet, right?
No, I didn't have it. I didn't need it for my major, but I was encouraged to take it and then I failed it. It was not fun. I mean, yeah, it happens.
Well, I would have failed it too, thanks.
No, don't say that.
Yeah.
Yeah, there'll probably be less coins in the future, but I'm trying to get people engaged right now, so. Goodbye. I think your dad's here.